In this presentation, we will introduce multi-objective evolutionary algorithms, or MOEAs. Most evolutionary algorithms are designed to optimize a single objective. In those problems, each solution receives one fitness value, and the goal is simply to find the best individual. However, many real-world problems involve several objectives at the same time, and these objectives often conflict with one another. For this reason, MOEAs were developed. Instead of producing one optimal solution, they generate a set of high-quality trade-off solutions that represent different compromises between the objectives. In this presentation, we will explain the main concepts of multi-objective optimization, the Pareto Front, the general MOEA algorithm, and two widely used methods, which are NSGA-II and SPEA2. Multi-objective optimization is important. In many practical problems, we must evaluate several criteria at the same time. A solution that improves one aspect may worsen another, so focusing only on one objective can hide important trade-offs. For example, a company may want to reduce costs while maintaining high quality. A transportation system may try to reduce travel time while also reducing fuel consumption. And an electric vehicle designer may try to increase driving range without making the vehicle too expensive. These objectives are related, but they are not always compatible. Improving one objective often requires sacrificing part of another. Because of this, the goal is usually not to find one perfect solution, but to find several good trade-off solutions. Then the decision maker can choose the alternative that best fits the available budget, constraint, or priorities. A multi-objective optimization problem can be formally expressed as minimize f1 of x, f2 of x, all the way to fm of x. In this formulation, x represents a candidate solution, the functions represent the different objective functions, and m represents the total number of objectives. Each objective function measures a different criterion of quality or performance. The problem may also be formulated as maximization or as combination of minimization and maximization objectives, but a minimization formulation is often used for clarity. The objectives may conflict, which means that it's not always possible to improve all objectives at the same time. As a result, the purpose of multi-objective optimization is not necessarily to find one global optimum, but to approximate to the Pareto Front. The Pareto Front is the set of solutions that represent the best possible compromises among the objectives.
Pareto dominance is a central concept in multi-objective optimization. A solution A dominates a solution B if two conditions are satisfied. First, A is not worse than B in any objective. Second, A is strictly better than B in at least one objective. This definition allows solutions to be compared without combining all objectives into a single weighted fitness value. For example, suppose the goal is to minimize both cost and time. Solution A has a cost of 100 and a time of 5 hours, while solution B has a cost of 120 and a time of 7 hours. In this case, A dominates B because A has both lower cost and lower time. However, dominance does not always exist between two solutions. Suppose solution C has a cost of 90 and a time of 8 hours, while solution D has a cost of 110 and a time of 5 hours. Solution C is cheaper, but solution D is faster. Therefore, neither solution dominates the other, and both can be considered valid compromise solutions. Solutions that are not dominated by any other solution are called non-dominated solutions. The set of non-dominated solutions forms the Pareto Front. This concept is fundamental because it replaces the traditional idea of a single fitness function with a comparison based
The
on
Pareto Front
dominance
is
relationships.
formed by the best available trade-off solutions. Each solution on the front represents a different alternative for the decision maker. A solution on the Pareto Front can't improve in one objective without worsening at least one other objective. Therefore, all solutions on the front are important because none is clearly better than the others across all the criteria. For example, in electric vehicle design, one solution may have low cost but lower driving range, while another solution may have high cost but greater driving range. Both can belong to the Pareto front if neither dominates the other. A good must pursue two main goals: converge, which means moving solutions close to the true Pareto front, and diversity, which means the distribution solutions across the front. Multi-objective evolutionary algorithm follows a structure similar to a traditional evolutionary algorithm, but it changed the way solutions are evaluated and selected. Instead of assigning a single fitness value, a multi-objective evolutionary algorithm evaluates each solution using all objective functions, ranks solutions using the Pareto dominance, and applies diversity preservation to avoid concentrating all individuals in the same region. In general terms, it initializes a population P with n candidate solutions, then evaluate each solution X using P using all objective functions. While the stopping criteria is not met, it ranks the solutions using Pareto dominance, estimate diversity, and select the parents. Then return the non-dominated solutions as the approximation to the Pareto front. And the key point is that selection is not based on a single fitness function. Instead, it is based on dominance and diversity. This enables the algorithm to maintain several high quality solutions that represent different compromises among objectives.
Now let's look at NSGA-II, which stands for Non-Dominated Sorting Genetic Algorithm 2. The process starts with a population and then all objectives are evaluated. After that, the solutions are organized using fast non-dominated sorting according to Pareto dominance. Then crowding distance is calculated to maintain diversity and avoid having too many solutions in the same area. Based on these criteria, the algorithm selects the solutions and applies crossover and mutation to create a new population. It also uses elitism, which helps preserve the best solutions between generations. Because of this process and its relatively low computational complexity, it is one of the most widely used multi-objective evolutionary algorithms. Now let's talk about SPEA2, which stands for Strength Pareto Evolutionary Algorithm 2. One of the main characteristics of this algorithm is that it uses an external archive to store the best solution found during the evolutionary process. It also assigned fitness based on the strength of each solution. In simple terms, this means that a solution is evaluated according to how many other solutions it dominates. Another important element is density estimation. This helps avoid having too many solutions concentrated in the same area of the Pareto front. Because of this mechanism, the algorithm can preserve diversity and maintain strong elitism. As a result, it can achieve better convergence and a better distribution of solutions across the Pareto front.
Here we have a comparison between traditional generic algorithms and multi-objective evolutionary algorithms, or MOEAs. So, a traditional generic algorithm searches for the best individual according to a single fitness function, and in contrast, a MOEA searches for a set of non-dominated solutions that represent different compromises. This difference changes the meaning of selection, evaluation, and also success. In a generic algorithm, fitness-based selection favors individuals with higher scalar fitness values, and in MOEA, dominance-based selection favors individuals that are not dominated and that contribute to a diverse Pareto Front. Diversity is also very important in MOEAs. In a traditional generic algorithm, diversity helps avoid premature convergence, but the final goal is still usually one best solution. In a MOEA, diversity is essential because the algorithm must provide multiple alternatives along the Pareto front. Also, elitism is commonly used to preserve high quality, non dominated solutions. Now we have an example problem. So, consider the design of an electric vehicle with two objectives: minimizing manufacturing costs and maximizing driving range. So, these objectives are in conflict because increasing driving range may require larger batteries and lighter materials or more advanced technology, all of which can increase manufacturing costs. So imagine we have a design A with manufacturing costs low, driving range medium, or a design B with medium manufacturing cost, high driving range, or design C, high manufacturing cost and very high driving range. So none of these designs is necessarily better than all the others. Design A may be attractive because of its low cost. Design C may be attractive because of its very high driving range. And design B may represent a balanced compromise. A multi-objective evolutionary algorithm will provide these alternatives as part of an approximate Pareto front, allowing the decision maker to choose the most appropriate design based on priorities.
Now, let's look at the typical components used in the multi-objective evolutionary algorithms. First, we have solution encoding depending on the problem. A solution can be represented using binary, integer, real valued, or permutation encoding. Then we have the genetic operators. For selection, tournament selection is commonly used. For crossover, we can use methods such as one-point crossover, uniform crossover, or simulated binary crossover, also known as SBX. For mutation, common options include bit flip mutation and polynomial mutation. Finally, the algorithm also requires some parameters such as the population size, the crossover probability, the mutation probability, and the number of generations. These components and parameters can be adjusted depending on the optimization problem.
Multi-objective evolutionary algorithms are useful in many fields where several criteria must be balanced. In engineering design, they can optimize cost, weight, strength, efficiency, and safety. In scheduling, they can minimize completion time, reduce delays, and balance resources. In supply chain optimization, they can minimize cost while maximizing reliability. In portfolio optimization, they can maximize expected return while minimizing risk. Include robotics, where energy consumption, precision, speed, and stability must be considered. Machine learning, where accuracy can be balanced against model complexity. Feature selection, where predictive performance is balanced against the number of variables. And transportation, where time, distance, fuel consumption, and emissions are relevant. These problems share the presence of multiple criteria that cannot be optimized independently. Advantage of multiple objective evolutionary algorithms. They can find multiple trade-off solutions in a single execution, which is valuable when there is no obvious best answer. They do not require combining objectives into one function with arbitrary weights, and they maintain a diversity across the Pareto front. They are also suitable for complex optimization problems with large, nonlinear, discontinuous,
for
On the other
difficult
hand,
search spaces.
multiple objective evolutionary algorithms also have limitations. They often require higher computational costs because multiple objectives must be evaluated and populations must be maintained. The selection process is more complex because it must consider dominance, diversity, and sometimes external hardships. Performance evaluation is also more difficult because it is not enough to measure one fitness value. The quality, convergence, and distribution of the Pareto Front must be evaluated. Despite these limitations, multiple objective evolutionary algorithms are highly useful when problems cannot be realistically reduced to a single objective. They provide a practical framework for understanding trade offs and supporting informed
Regarding
decision making.
conclusions, these tools are powerful for solving problems with multiple conflicting objectives. Instead of producing a single optimal solution, they generate a Pareto front that allows different alternatives to be analyzed. This is useful because many real world decisions require balancing cost, quality, performance, efficiency, risk, and other
Non-dominated sorting
criteria.
genetic algorithm 2 and the strain Pareto evolutionary algorithm 2 are two classic and widely used approaches. The first one is based on non-dominated sorting, crowding distance, and elitism, while the second one is based on an external archetype, strength-based fitness assignment, density estimation, and strong elitism. The main difference between multiple objective evolutionary algorithms and traditional ones is that the first ones use Pareto dominance and diversity preservation during selection rather than rely on one
These
scalar
tools
fitness
are
function.
especially valuable in engineering, transportation, machine learning, robotics, economics, and planning because these areas often involve objectives
By
that
offering
compete
a
with
set
each
of
other.
balanced solutions rather than imposing a single answer, multiple objective evolutionary algorithms help decision makers understand trade offs and choose the alternative that best fit their priorities.